Arnold-Bohm effect. So, uh, so what they measure in a fiber optic gyro or ring laser gyro, they're measuring a phase shift. An Arnold-Bohm effect, even if you have a solenoid, which is basically a copper wire, donut of uh, metal wire charged up, even though there's no detectable magnetic field on the outside of it, it will still cause this phase shift of electrons. It'll change the spin of an electron. It'll change the phase of a photon, right? So you would actually, if you rotated one of these inside of a magnetic field, assuming the Arnold-Bohm effect, it would actually cause a phase shift, and you'd be able to measure the rotation. You'd also be able to measure as you move along the Earth. It would also cause a phase shift. So, I mean, we can come up with alternative hypotheses on why some device does some certain thing. I mean, that's not really an issue.
Yeah, I was just wondering about the mechanicals, because there's a lot of people that rave on, oh, mechanical gyros exist, therefore ball art exists. And I started looking into it, and I just couldn't find anything about the
It's
causation.
hard, dude.
Yeah.
Yeah, so now Matrix, I looked for. I mean, way back when we first started doing this, like we looked really hard to find anything. It's really hard, dude, because it was classified. And then there's a point in time where they like, yeah, because it was used for like the military, right? It was initially used in the Navy. So that mechanism, like the device, and they also had it hooked up, like so, like the way it worked in a naval ship was they had the gyro compass, but the gyro compass um, was calibrated using a magnetic compass. They were actually electronically, not with like digital electronics, so like analog. They were hooked to each other, so they would give like a uniform reading. So you would actually have both. So you'd have the gyro compass and the magnetic compass at the same time, and they would try to figure out like their heading and shit from that. They didn't rely on just one or the other. But like the whole Sperry patent, dude, that all that shit was like classified. So only one company made them, a company named Sperry Gyro Compass. Right. So it's Sperry. So they made these gyro compasses, but like their inner workings and all that crap were like classified. The only thing we could ever get, we did get something that inside it, it's basically like a ball inside of, what do you call it? Inside of a bunch of gimbals. But the compass that's inside, but the wheel, there's a wheel inside of it, and that wheel is the ball itself is like a vacuum chamber because to prevent drag and to prevent torque from air drag, right? So yeah, there's not a lot on it. It's pretty kind of black box to a degree.
Yeah, it was just really interesting. Like I'm looking up, like I didn't go too far out of my way, but I was looking it up, and that's what I'm sitting there thinking. Okay, is this flywheel made out of something in particular? Is it due to torque vectors on the flywheel itself that's generating some kind of magnetic flux within inside it? Because the one video I did see, it was from FE Core, which I think Eggshells posted up, and yeah, it was just very interesting the way the device behaved. They actually set it at west, south, and east, and timed it to see how long it tracked back to north. And at south, it took like, was it 84 minutes or 87 minutes to get back to north. But it behaves exactly the same way as a standard compass. So that to me says that it is following some kind of magnetic field, whether it's super duper weak or not, and that's why it takes so long to track. I don't know, but my interest was more in the causation. What is causing it to track back to magnetic? So there must be something magnetic in it, not gyroscopic. So yeah, I was just wondering what the...
Well, it'll become magnetic, right? So if it creates a current, there's going to be a magnetic field. It's just a consequence.
Yeah, I just didn't know how it did it though. That was all. That was my thing.
Yeah, so
magnetic.
any accelerating piece of metal in a magnetic field, which a rotating disc is, every part of the disc is accelerating because it's changing direction, it's spinning, right? So
Yep.
the whole entire disc is accelerating in a magnetic field. But the thing, like, just to go back to like the FE core, it's when you're talking about the FE core gyro compass. People never realize that the very first thing was first test. They go, he says, this is spinning. This went the wrong way. So it rotated the wrong way. When it went to align itself, it went in the wrong direction. But if the alignment is caused by a torque by the rotation of the Earth, then that's impossible. You
Yes.
understand? Because it went the
Yes, because
opposite
that's what I
direction
saw
of the
that, yeah.
force.
Because he explains it all, that it should technically go this direction all the time, whereas in actual fact, it goes this direction, this, and showed all the different ways and things that it had done. They explained it all, but yeah, I was just wondering about the initial causation. So now that you've said that the high spinning disc running through a mag field, yeah, that makes a lot of sense.
And you know what? And the only way it's not going to get a torque from the magnetic field is if it's aligned with the magnetic field, right? So if it's running parallel to the magnetic field, the direction of the disc, right? So the flat part is parallel with the magnetic field, then you won't get a torque.
Yep.
It's only when it's perpendicular. So it's going to try and right itself perpendicular using the same principle, right? There's a torque caused by the Lorentz force that's causing the freaking gyro to process it and align itself until it doesn't experience a torque, and that would only happen is when it's aligned north and south.
Oh, cool. Cool. All right, cheers, man. Thank you.